Good morning. My name is Jiří Borovička. I'm working at the Astronomical Institute of the Czech Academy of Sciences. And I will talk today about the Geminids observed by the European Fireball Network with this common work with Pavel Spurný. Okay, first few words about the European Fireball Network. It was established already in 1963. It covered Czechoslovakia, Western Germany, and parts of other countries. And the network was, of course, modernized many times. The last big modernization occurred about 2014, when so-called digital autonomous fireball observatories were introduced in the Czech and Slovak parts of the network, and in addition, one of such observatory is in Austria and one in Germany. We also have a cooperating network in the Netherlands using the same optics and operated by the Dutch Meteor Society. Here is how the digital autonomous observatory looks like. On the right, it's with a covered door, but open the cover of the lenses. There are two Canon 6D cameras with Sigma 8mm fisheye lenses, and there is a radiometer, some photomultiplier used for precise photometry. Here is with the open door, which some operating panel which one used to open the cover manually and so on during the maintenance, but normally the cameras work fully automatically. Here is the current map of the stations of the digital cameras. We have 21 stations currently here in the Central Europe. Few words about the Geminids. As you know, it is the most active annual meteor shower with maximum around December 13. It has a short period with low perihelion distance, only 0.14 astronomical units. The parent asteroid Phaeton was discovered to be weakly active at perihelion and has a dust trail near its orbit. Nevertheless, the current activity of Geminids cannot be explained neither by the activity, neither by the dust trail, because these are very low and cannot account for the total mass of the stream. So many open questions remain about the origin, evolution, and composition of Phaeton. If it's a regular asteroid moved closer to the sun, or some special type of asteroid, or some former comet which is only weakly active now. And consequently, we don't know about the formation mechanism and evolution of the Geminid stream. For this work, I first used the Fireball catalog we recently prepared. It contains more than 800 fireballs manually produced, observed in 2017-2018. It will be published soon in Astronomy and Astrophysics. There are in fact two papers, one about the catalog and second about the analysis. And a small part of the analysis is also the Geminids, the radiance and orbits of 38 Geminids. And for this talk, I selected more meteors, 66 most precise Geminids observed in 2016 up to the last year. I have to say that the weather was not very good for the Geminids in neither of the years. It was mostly cloudy, but nevertheless, there were some periods of clear sky, at least on some stations. Here is just the map of the observed Geminids. The symbol size is proportional to the maximum magnitude. The point corresponds to the point of the maximum magnitude, so we cover part of the Central Europe. Some examples. This is the brightest observed Geminids, about -12 magnitude, produced by meteorites of 800 grams and reaching the end height of 40 kilometers. The interruptions are intentionally produced by LCD shutter to enable the measurement of the velocity. Another similarly bright Gemini, even more massive because this was longer. The radiant was of lower elevation at this time. And here, the longer dashes are the time marks for measuring the absolute time. And another one, or sky image of painter Gemini playing during the full moon, and you can see there were some clouds. The exposure time is 35 seconds. So now the results, the radiant motion in right ascension. Here is the plot of our Geminids, the geocentric right ascension as the function of solar longitude, and compared with some data published on the IAU Meteor Data Center from other authors. Here we can see the dashed line is our hit. We observe a little bit higher right ascensions for any solar longitude than other authors. For the declination, the agreement is quite good. The geocentric velocity, there is no trend with solar longitude, but the actual spread of our data is even lower than the spread of the mean values from other authors. But for example, this measurement is from meteor radar, so much more meteor days. When the radiant was corrected for the motion, we plotted the position of the radiance normalized to the time of the maximum. You can see the radiant is quite compact. 85% of individual radiants are within half of degree of the mean radiant. Here the symbol size is proportional to the mass of the meteoroid, from less than 1 gram to more than 1 kilogram, and you can see there is a trend of larger meteoroids having a little bit larger right ascension, so maybe observed larger right ascension than other authors who observed fainter meteors. Here is the similar plot, but color code are the semi-major axes of the meteoroid, and there is non-random pattern. Again, the reddish color are lower semi-major axes, and they tend to have higher right ascension than the meteors with larger semi-major axes. This is the same plot in ecliptic coordinates, which is probably more correct way to do it. So on the x-axis there is a difference of ecliptic longitude to the solar minus the solar longitude. On y-axis is the ecliptic latitude, and we can again see the meteors with lower semi-major axis are to the right. We also compared the radiance distribution for different periods. The blue points are for 1 day around the maximum. Red ones are before the maximum. Black ones after the maximum. And you can see the spread of the radiance is higher before the maximum than during and after the maximum. Here is the radiant and inclination. This is the expected results. The higher is the ecliptic latitude, the higher is the inclination of the orbit. This is natural. Another trend is the argument of perihelion, although clear dependence. In this case, I'm not sure if this result is trivial or not, but there is a very clear trend, dependence of the position of the radiant and the argument of perihelion. Now plot of the orbits. Here is the eccentricity versus semi-major axis. Here is the position of the phaeton, and we see the orbit distribution is not random. There is what I call the core. They have similar semi-major axis as phaeton, but some little bit lower eccentricity and also a little bit larger perihelion distance. This is the line of constant perihelion distance. And there is a wing with larger semi-major axis and similar perihelion distance like Eton. I plotted also the model values computed by Galina Ryabova but for much smaller meteoroids. And there is good overlap in this part, but we observed also larger semi-major axis than predicted by the model. And maybe more importantly, the model predicts, due to pointing Robertson drag, that smaller meteoroids will have lower semi-major axis. But at least in our mass range, we observe the opposite trend. Most of the larger meteoroids have lower semi-major axis than, and the larger axes are only in for faint meteor. Here is the function, the semi-major axis as a function of photometric mass. For lower masses, we have all range of semi-major axes, but for larger meteoroids, only smaller axis. Here is the inclination. Most of the inclinations are about 23-24 degrees, which is in accordance with the model. Eton has some lower inclination, but there are some meteoroids with similar inclination, especially in the core. There are some others with some a little bit higher inclination. There is also a dependence of argument of perihelion over semi-major axis. Some trend. For illustration, here are 3 Geminid orbits with different semi-major axes compared with the orbit of Eton. And I plotted the histogram of semi-major axis. There is small statistics, but there seems to be two gaps, and they almost overlap with 2 major resonances, 8-1 with Jupiter and 2-3 with the Earth. But when we look at the error bars of the semi-major axis, still the precision of the data is not good enough to really confirm that there are gaps in the resonances. And other point is that there is no dependence of semi-major axis on solar longitude, so the core meteoroids with lower axis and the meteoroids with larger axis both are encountered during the whole duration of the stream. Final note about the physical strength of Geminids compared with other showers. It is not new result, but demonstrated here. Here is some measure of the strength of meteoroids depending on the dynamic pressure encountered during the trajectory. So the higher value, the stronger meteoroids. Here is the different parameters. So there are mostly cometary body orbits and asteroidal orbits. And Geminids are, as is well known, among the strongest meteoroids, comparable only to Eta Virginis. And in some other showers, especially Taurids or Alpha Capricornids, we need the trend that larger meteoroids are weaker and smaller are stronger. But in Geminids, this trend is not present. In fact, some of the weakest ones are the small ones. So the summary. The Geminids have a quite compact radiant area. There is a correlation between radiant position, semi-major axis, and argument of perihelion, which I think is new finding. The semi-major axis extend up to 1.39 astronomical units, which is more than the cometary model Ryabova predicts. he assumed that the stream was formed 2,000 years ago during the short period of time. We also have found that larger semi-major axes have larger meteorites have smaller semi-major axes than the small ones, at least in mass range between 1 gram and 1 kilogram, which is not expected, but it was already mentioned by Pavel Spurný in 1993. And centimeter-sized Geminids are physically strong, comparable to ordinary chondrites. We plan precise video observations if the weather is good to extend to this work with fainter Geminids. We started detailed modeling of atmospheric fragmentation of larger Geminids. Spectroscopic analysis was already done also by other people for video observations, but we have also some photographic spectra. And most importantly, it is needed some modeling, formation, evolution of the stream, and compare the result of the modeling with the observed orbit. Thank you very much.